So first of all, quantization. Quantization is the process of transforming the sample amplitudes m of nts of a message signal m of t into discrete amplitudes v of nts taken from a finite set of possible amplitudes. If we have a data signal m of t, such as the one shown here, as we've seen in the previous chapter, we can use sampling and read off the samples every ts seconds. We saw in the last section how we could map these to rectangular waveforms or impulses or something else. But here we're going to do an additional step, which is quantization. In the case of a system with quantization, the amplitudes can't just be any value at all, but must be selected from a finite set. In this case, in this figure, these red dashed lines indicate where the acceptable values are. And so at a given point in time, you will choose the quantization level that is closest to you. So for example, at time 0, your sample value is right here. You're closer to this dashed line than to this one, and so this is the value you choose. Now in some cases you'll go up to the nearest one, sometimes you'll go down. It just depends on the value. For example, at time, let's see, this is TS, 2TS, 3TS, you actually go down to the nearest value. There is an additional value here at time 0, you just can't see it because of the axis. Now in this particular example, all of these levels are equally spaced, and so this is a case of uniform quantization. Now an important observation regarding quantization is that quantization produces error that is unrecoverable. Once you take this step of quantization, there's no way to go back. And that's pretty clear just from thinking about what you're doing. Again, here is our samples, and here is our quantized outputs. Once you are limited to these particular values, you don't know how you got there. You do know that you were closer to this value than you were to any other value, but you don't know the actual value of your signal. And so there's not going to be any way to rebuild your signal without error. This is independent. This is true no matter what the sample rate is. There's no way to fix this by sampling more. Every single sample is going to have this problem, that information is lost. And in fact, we can actually calculate the quantization error if we know both, if at the transmitter we know the original message as well as our quantized values. And it's simply defined as the difference between the quantized outputs and the original samples. For example, at time 0, V is this value here, and M was this value on the curve. The difference is a positive quantity, and it's given by this value right here. Now, if we have L equally spaced quantization levels, and their step size is delta, then it follows that delta should equal 2 over L max over T, absolute value M of T. Why is that? Well, because if you look at the max of the absolute value of M of T, that's the largest positive value you could have, and also bounds the largest negative value you have because of the absolute value. And so 2 times that max value will give you the total range from top to bottom. And we basically need to divide this up into L levels, each of which have step size delta. So we'll have delta times L is equal to 2 times that max. And so dividing by L, we get delta as 2 over L times the max. In addition, if our step size is delta, then delta over 2 will be the worst case quantization error. Now this neglects a little bit of something. This assumes that we really have a max value that we can be assured of having in all times. But if that's the case, then delta over 2 really is the worst case quantization error. If you have some value, you're always going to choose the one closest. And the worst case is right when you're halfway between 2 values, and that's when you get delta over 2. All right, so we have these results.